Please let us wait for 2 more minutes and let's see if anybody else is joining, and then we will start the live session. Okay, so let's start the live session. So today, were you present in the last live session? People who are here today, did you attend last week's Saturday live session by me? Week 1. If not, then my name is Smita Mujumdar, and I'm a PMRF scholar in IIT Roorkee, Department of Biosciences and Bioengineering. So I will be conducting classes. Let me just share my screen. Second. Okay. So okay. You can see my presentation. You can see my presentation.
Yes, ma'am.
Okay. So today in week 2, I guess you have already studied about characterization techniques. So what kind of characterization techniques you have learned in this week? Anybody can tell a few names? Characterization techniques. Characterization techniques that you have learned in this week. Yes. Spectroscopy, correct. Spectroscopy, specifically what kind of spectroscopy? Specifically what kind of spectroscopy? Yes, okay. UV visible spectroscopy, and what else? Fluorescence spectroscopy, and what else? DLS. What is the full form for DLS? Full form for DLS? No, not differential light scattering. It is dynamic light scattering. Dynamic light scattering. What else? You have learned zeta potential, UV visible spectroscopy, FTIR. Then you have learned fluorescence spectroscopy, which is also known as another name for fluorescence spectroscopy we will see here, which is also known as photoluminescence spectroscopy, PL spectroscopy. And DLS, zeta potential. And what else? XRD, X-ray diffraction. And is the video for AFM uploaded? Atomic force microscopy. AFM? AFM is uploaded, atomic force microscopy.
Yes, ma'am, it is uploaded, but I haven't gone through that video.
Okay, so that is, I guess, in week 3.
Yes, ma'am.
Okay. Thank you. So basically, what we will be talking about is today we will be talking about a few you already have read in details, but some extra details which were not there, or maybe I have not exactly seen the videos, lecture videos, so I don't know how much explanation was provided. Please let me know if these explanations were provided or not, and I will elaborate a little bit more on processes which we have learned. Mostly you have been taught from nanomaterial point of view, but we all know these spectroscopic techniques are basically for organic molecules, okay, as well. So today we will be learning about quantum dots. As far as I remember, in week 1, you guys were taught about carbon dots, where in one slide there was a comparison between carbon dots and quantum dots. So any idea about what quantum dots are? Any idea about what are quantum dots? So quantum dots are semiconductor nanocrystals. So what do you mean by semiconductor nanocrystals? What do you mean by semiconductor nanocrystals? Semiconductor means we have 3 kinds of materials. Like, what are the 3 kinds of materials? One is metal, which is a conductor. Then we have semiconductor, and then we have insulators. Right. So metal have a conduction band with free electrons. Metals have a conduction band with free electrons. When you are providing energy, these electrons jump to higher level and then come back down. So that is how the conduction happens in metals. For semiconductor, what happens? For semiconductor materials, you have a conduction band and you have a valence band, and then you have a conduction band. So what happens when you provide energy? Then from the valence band to conduction band, the electrons jump and come back. So that is how semiconductors transfer, like conduct. And the other one is insulators. So insulators, we will be talking about a term called band gap. Have you heard of the term band gap? Have you heard of the term band gap? Have you heard of the term band gap? Anybody could answer if they've heard it. Okay, so I will be talking about the term band gap. So first we'll be talking about quantum dots. Now in carbon dots, what you read, carbon dots are made of materials, carbon materials. So carbon dots are also compounds which you can make from, second. So carbon dots are made of materials. Yes.
இல்ல நம்ம ஒரு நாளும் பார்த்தது இல்லல்ல மேபி எப்பவுமே
Okay. So carbon dots are material made from, you can make from natural sources. Basically, it is non-toxic carbon dots. The biggest advantage of carbon dots, non-toxicity. So quantum dots and carbon dots are basically similar in they're basically similar. Both size ranges are same, but difference is quantum dots are semiconductor nanocrystals. So semiconductors means what? They are made of components. They're usually composed of elements from groups 2, 6, such as cadmium, selenium, cadmium, sulfur, or cadmium, tellurium. Okay, so these are all heavy metals. So these are all heavy metals that we are talking about. 1 second. So we are talking about heavy metals. So in heavy metals, what happens if you use it for biological purposes? There will be toxicity. Okay, so another group of elements which are made of quantum, which makes quantum dots, is group 3,5, such as indium phosphor or indium, or groups 4,6. Second. Groups 4,6. What is there in group 4,6? Just such as lead, selenium. So the shell is usually composed of Z and S to improve the optical properties. So quantum dots, and what you have a quantum dot core, which is basically made of two heavy metals. It could be cadmium, it could be selenium, it could be tellurium, it could be made of indium. Okay. So, and why do you have a shell? This here in the picture you can see that you have a quantum dot core. So the core is usually the elements that is mentioned in this second point, and the shell is made of Z and S. So this shell actually helps in improving contrast quality. So these are also fluorescing materials, right? So these fluorescing materials help in this ZNS shell will improve your optical fluorescence. So it will increase your quantum yield. I think you have learned quantum yield in fluorescence spectroscopy. You've learned quantum yield. Quantum yield. So this ZNS shell is basically to increase the quantum yield of your nanoparticle. Capping is done to enable improved aqueous solubility for biology related applications. So if you have to use quantum dots for biology related applications, so what you have to do, you have to cap it so that it is not recognized as foreign by the body. So, and also to make it aqueous soluble. Okay, because quantum dots, they're made of heavy metals, so mostly they will be not have poor solubility in aqueous solvents. So to increase your solubility, as well as to also make it the stealth technology we talked about, PEG. So that is there. And also if you have to surface functionalize it, as here you can see in the picture. One second. Here in the picture, you can see that you can surface functionalize the quantum dot with some hydrophobic drug, protein, some drug which is hydrophilic, then antibody, so that it can be specifically targeted to a cell. Okay. But the biggest disadvantage of quantum dots is that because it is made of heavy metals, there could be toxicity. So in biology related applications, the quantum dots are used, but carbon dots are more preferable. They are more safer option for toxicity related results. So how are QDs different from bulk semiconductors? So here we are talking about what? So here you can see an example of a bulk semiconductor, which is shown in black here. So in the bulk semiconductor, this VB you see, this is your valence band, and CB is the conduction band. So can you see the gap between the two? The gap is less. But when you're decreasing the size of the particle, you slowly see that here you can see range quantum dot 6 nanometer to 2 nanometer. So red one is 6 and the green one is 2 nanometer. And you can see here that with decreasing size of the quantum dot, there is an increase in band gap. Now what is band gap? Band gap is the gap between the valence band and the conduction band is known as band gap. And energy band gap is the energy which is required by an electron in the valence band to overcome this band gap and get excited to the conduction band. That is known as energy of the band gap. Okay, so as you can see that with decreasing size, the band gap considerably increases a lot. You can see in the bulk it is small, but with the decreasing size, the band gap increases. So what it means? It means that with decreasing size, you need more energy to excite an electron from the valence band to the conduction band. Okay. So this is one of the biggest thing observed for quantum dots. What is happening? The band gap increases with decreasing size. Now, what is this phenomena called? This with decreasing size, the increase in band gap. This is called quantum confinement. So what is quantum confinement? In simple words, electrons are confined. That is, they occupy less space than bulk. Hence, valence band and conduction band potentials are shifted more positive and negative respectively, which results in high band gap. So when you are decreasing the size, what is happening? The electrons, they are occupying less space than bulk. So in bulk, you have more space, but with decreasing size, they have less space. So as a result, what happens? The valence band shifts more positive and the conduction band shifts more negative, respectively. And the band gap increases. This is known as quantum confinement. So here a term comes which is known as exciton Bohr radius. So what is an exciton Bohr radius? So in the valence band, you will have a bound electron hole pair. So they are in their lowest energy states, which is called a exciton. Okay. So here in the picture, you can see this is the lower band is the valence band. Over here, you can see solid circles. These solid circles are bound electron hole pair. They are in their lowest energy state, that is, they are very stable. And these single bound electron hole pair in the valence band, they are called exciton. Now what happens? An exciton can form when a photon is absorbed by a semiconductor. So this bound electron hole pair, what will happen? When it has a particular wavelength which it can observe to get excited. What will be the wavelength? I said that the gap between the valence band and the conduction band is called band gap. So the energy required to get excited, so that will be the wavelength of this particle, of this electron hole pair. So when the electron absorbs a photon, which helps in overcoming the energy of this gap, then an exciton can form. So what is an exciton? Exciton is an electron hole pair. When it is not excited, then it is just electrons. When it gets excited, when the electron gets excited to the conduction band, you can see there is a gap in the valence band. Okay. So this gap is known as hole, which is positive charge. So your electron is negative charge and this hole is positive charge. So this electron hole pair is called an exciton. The average distance between an electron and hole is called exciton Bohr radius. So the distance, average distance between this electron and this hole pair, this is known as exciton Bohr radius, also referred to as de Broglie wavelength of the electron. Okay. So what is happening when we are reducing the size? In a semiconductor crystallite whose size is smaller than twice the size of its exciton Bohr radius, the excitons are squeezed, leading to quantum confinement. What it means? Here we go back again. You can see this red line is showing your exciton Bohr radius. Okay, the distance between the average distance between the electron hole pair. So if the crystalline, the quantum dot size is smaller than twice the size of its exciton Bohr radius. So what is happening? One second. So what is happening? If the size of your particle is smaller than twice the size of this distance, then what is happening? The excitons, that is the electron hole pairs, they are squeezed in a small space. This is leading to quantum confinement. A particle behaves as if it were free when the confining dimension is large compared to the wavelength of the particle. During this state, the band gap remains at its original energy due to a continuous energy state. However, as the confining dimension decreases and reaches a certain limit, typically in nanoscale, the energy spectrum becomes discrete. As a result, the band gap becomes size dependent. This ultimately results in a blue shift in light emission as the size of the particles decreases. Did you understand what is happening? What is quantum confinement? How the band gap is increasing with decreasing size? Is it understandable? Do I have to repeat anything? Okay. So now we come to quantum confinement. So what happens, the smaller you make the crystal, the higher the energy of the electron will be. Obviously, we saw that the band gap increases, and I said that you need, the band gap is the energy, amount of energy an electron needs to overcome that gap and gets excited to the conduction band. So the smaller size you make, the bigger will be the band gap. That means more energy it will require to get excited. So the kinetic energy of that electron will get increased. The uncertainty principle states that the more precisely one knows the position of a particle, the more uncertainty in its momentum and vice versa. So we all know that uncertainty principle says if you know the position of the particle, then there is uncertainty in the momentum. If you know the momentum of the particle, then you don't know the position of the particle. So you know only one parameter. So therefore, the more spatially confined and localized a particle becomes, the broader the range of its momentum or energy. This phenomena of increasing excitation energy with decreasing crystallite size is known as quantum confinement. So when you are decreasing the size of the particle, the band gap increases. You need more excitation energy to excite electrons to reach the conduction band, to form the exciton, that is the electron hole pair. This phenomena is known as quantum confinement. Now we come to carbon dots. So what are carbon dots in comparison to quantum dots? What is happening? Carbon dots are small carbon nanoparticles. They are less than 10 nanometer in size. Quantum dots are also small nanoparticles, less than 10 nanometer in size, with some form of surface passivation. So they were first discovered by Zhu et al. In 2004 accidentally during the purification of single-walled carbon nanotubes. Have you heard of carbon nanotubes? Did you hear of carbon nanotubes? Anybody who has heard of carbon nanotubes? Okay. So can you tell me what carbon nanotubes are in brief? In brief, anybody can tell me what are carbon nanotubes? Because I will tell you a good example of carbon nanotube application, which is part of the characterization technique. Most oftenly used nowadays in characterization techniques. Okay, so carbon nanotubes are what? Okay, so they are basically graphite is multi-layer sheets, graphene single layer, stacks of graphene sheets make graphite. Graphene is single sheet. So graphene, if you roll it, there is a term called rolling vector in carbon nanotube. Depending on the direction you're rolling the graphene sheet, you get a carbon nanotube. That single wall carbon nanotube is made of a single graphene sheet. You're correct regarding the graphite one, but it will not be a single walled carbon nanotube. Graphite will give you multi-walled carbon nanotubes. Because graphite has multiple, multi-walled carbon nanotubes for graphite, and for graphene you will get single-walled carbon nanotube. So basically, if you have single wall carbon nanotubes, so you have graphene sheet, you roll it. There's a term called rolling vector. So you roll it in particular direction, and depending on the direction you're rolling it, you get different conformations of carbon nanotubes, armchair, zigzag, like that. There are different conformations, and depending on the conformations of your carbon nanotube, you have the what kind of characteristics it will show, whether it will show metallic behavior, whether it will show semiconductor behavior. So carbon nanotubes, they are conducting materials, and basically they can show two types of behavior. One is metallic behavior, one is semiconductor behaviors, and this is depending on how the sheets are rolled. Okay, so these carbon nanotubes, so this person Zhu et al, what he was doing is he was purifying single wall carbon nanotubes. Now, single wall carbon nanotubes are very difficult to synthesize. So accidentally, then he discovered this carbon dots. So this discovery triggered extensive studies to exploit the fluorescence properties of carbon dots. Second. Okay. So what are carbon dots? They are biocompatible. They have small size with relatively large surface area. They're photostable and having photoluminescence properties. Okay, so we all know that carbon dots, they fluoresce, they give very good fluorescence, but carbon dots, carbon dots are currently emerging as a class of promising fluorescent probe on account of the low photo bleaching, versatile surfaces, and excellent biocompatibility, because they're basically made of carbon. So it is very much biocompatible. Your body can break it down, and they're small in size, so there is no problem in renal clearance as well. So carbon dots, they are currently emerging as a very, because you will see a lot of papers in which they have used carbon dots. Biggest application of carbon dots, can anybody tell me? You have already read any application, biggest application of carbon dots in biotechnology?
Drug tracking.
Drug?
Tracking any drug inside the.
Yes, you can track drugs, you can do bioimaging purposes, and another thing that you can do is sensors. Sensors nowadays, out of the body, sensors nowadays are being developed using carbon dots. Like you have, like last time we talked about gold nanoparticles, which gives colorimetric sensors. Carbon dots, similar property, similar thing. It will show that there is some aggregation, and it will the fluorescence will quench. So you will get sensors with on-off technology. So carbon dots, when you basically coat the carbon dot with a material. Have you heard of the fret phenomena? Fret phenomena. F-R-E-T, fret. So fret is basically energy, fluorescence resonance energy transfer. It is basically a resonance between two fluorophore. You have a fluorophore and a quencher. They're very close to each other. So fret only occurs when your fluorescence and fluorophore and your quencher is less than 10 nanometer, at a distance of less than 10 nanometer. If your distance between the two is more than 10 nanometer, then fret will not occur. So fret occurs at a distance of 10 nanometer or less than 10 nanometer. So nowadays what is happening is carbon dots, they are currently being developed in which you have taken the carbon dot, which is a fluorophore, and then you're coating it with a material which is a quencher. Okay, so So you have a quencher surrounding the carbon dot. Now this quencher, when you are inserting, then you are functionalizing it with something so that it gets targeted to a particular body, cell of the body. For example, you're targeting it to a cancer cell. Okay. So, so that is how it is. You can even diagnose like that in body diagnosis. So what they're doing is they suppose you are targeting it in the body and it enters the cell, and then we know that we have GSH. You have heard of GSH? In the body, GSH. Yes. So GSH, this we know that cancer cells, they produce a lot of GSH. So this GSH will react with your quencher, and your quencher, the shell. So basically, in quantum dot, I showed an example right now. You remember I showed this example of quantum dot where you have a core and a shell. So this core is carbon dot, the shell is your quencher, and whatever wavelength. So we have an emission wavelength and we have a excitation wavelength and an emission wavelength. So the whatever is being emitted by your carbon dot, it is getting absorbed by your quencher, and your quencher is not giving out any excitation wavelength. So that is the FRET phenomena, because the absorption spectrum of the quencher is the absorption spectrum of the quencher and the emission spectrum of the carbon dot, that is overlapping at one place. Okay, so that is how the FRET phenomena occurs, and your carbon dot fluorescence is quenched. When your shell is being degraded, suppose you have a material which gets degraded by GSH. The reduction takes place, redox reaction takes place, GSH becomes GSSH, and GSH becomes GSSG, and your shell gets degraded. Okay, then what will happen? Then whatever emission is given by the carbon dot, that is not being absorbed by the shell anymore, quencher shell anymore, because the quencher has been degraded. So then your carbon dot will start fluorescing again. It will switch on. So this is the off on strategy, which is currently you will find a lot of papers. You can search any paper and try to read a paper on how they use this on off technology for designing diagnostic. They're trying to detect. In this case, you are detecting GSH sensing in cells. Okay, so fluorescent CDs have attracted increasing attention due to their potential application in sensing, catalysis, and biomedicine. Heteroatom doped CDs have enhanced fluorescent properties. Okay, what does this sentence mean? Heteroatom doped CDs have enhanced fluorescent properties. Any idea? Any idea? So heteroatom doped means carbon dots, they have less, the intrinsic fluorescence is less. The quantum yield of the carbon dots is less when you do not dope it. So that is why if you dope the carbon dots, there are two kind of doping. One is known as N doping, the other known as P doping. N doping means you are putting more electrons in your material. Okay, so N doping and P doping is positive. You're putting more holes in your electrons. Sorry, in your carbon dots. So you have a concept of N doping and P doping, and sometimes both doping are done. P and both doping are done. That is why they're saying heteroatom dope. So this doping basically enhances the fluorescent properties. It increases the quantum yield of your carbon dots. So the sensitivity of sensing or catalysis or bioimaging, it increases. So synthesis of carbon dots. Synthesis of carbon dots, you can see there are two methods of synthesizing carbon dots, top down and bottom up. In top down, you can use laser ablation, chemical oxidation, arc discharge, sonication, and electrochemical oxidation. And in bottom up approaches, you can use thermal carbonization, microwave synthesis, acidic or alkaline dehydration, plasma treatment, and hydrothermal treatment. In which I think you mostly what has been discussed is microwave synthesis and hydrothermal treatment. Okay. So microwave synthesis and hydrothermal treatment, mostly hydrothermal treatment is preferred for bottom up. And do you know what is thermal carbonization? Thermal carbonization, it is a, yes, correct. Nitrogen atom or sulfur atom for benzene in heteroatoms. Benzene. You're making the carbon dot from benzene. You separately, you can dope with any material. You can dope with nitrogen, you can dope with phosphorus, you can dope with boron. Basically to increase the quantum yield. So coming to quantum yield, anybody can tell me what is quantum yield? What is quantum yield? Anybody? What is quantum yield? Quantum yield. For a fluorophore, you're exciting the fluorophore with a particular number of photons. But when it is absorbing a particular number of photons, but is it emitting the equal number of photons? So quantum yield is basically the number of photons emitted by a fluorophore divided by the total number of photons absorbed by the molecule. So your quantum yield will increase when the denominator is less. It's a very big calculation of how to, measure quantum yield. It's a very big calculation. So you can check it one time how to determine quantum yield, how experimentally, like you get the value of your excitation maxima, emission maxima, and then how you can calculate your quantum yield. It's a very lengthy procedure. So you can check it out one time online. And if you have any questions regarding that, you can ask me in the next class. And if you want any presentation prepared on how to, calculate quantum yield, I can try to incorporate that as well. So, basically, thermal carbonization is you take your carbon material with which you will make your carbon dots, and then you just burn it to char. So you keep it, you burn it at very high temperature, and it will completely till it's charred, and then you purify it and get carbon dots from the solution. Okay, so in hydrothermal, you can see this is the hydrothermal synthesis reactor. So in the hydrothermal synthesis reactor, what do you have? You have you have the reactor body, you have the reactor cap, then you have a locking rod. So basically, you can see the the rod goes inside, and then you tighten the lid. You have to tighten the lid. Okay, so that the pressure is maintained inside. Then you have hydrothermal synthesis reactor chamber cap, and you have hydrothermal synthesis reactor disk. Okay, so this cap is which is the cap is the one which is screwed onto this reactor body, and you place a material in this. So for whatever material you are using for synthesizing of carbon dot, you make a solution of it, pour the solution in water. If you are using a green synthesis method, suppose you're synthesizing carbon dots from leaf. So you wash the leaf very nicely, and then what you do, you put it inside this reactor and pour a little bit of milky water. And then you put the chamber cap, and then what you will do, you have to put this synthesis reactor disk. One goes at the bottom, and one goes at the bottom of this hydrothermal synthesis reactor, and the other goes at the top. If you do not put this, if you forget to put either of the hydrothermal synthesis reactor disk, what happens is that this is made of Teflon. So this will expand at high temperature, because usually these hydrothermal processes, they're carried out for longer durations, like 6 hours, 10 hours. So, and at a temperature of 180 degree, 200 degree, sometimes even higher, depending on whether your Teflon can withstand the temperature. So you get different containers which can withstand different temperatures. So you should always clarify whether your Teflon, this reactor, this synthesis reactor can withstand the temperature, working temperature. So if it can withstand maximum 200, then you should not even keep the reactor at 200 degree in the autoclave for 6 hours or 8 hours or 10 hours. Then also it can, you know what happens, it expands and the reactor gets destroyed. So what happens is, what you have to do is, what you have to do is, you have to keep it less than 200. If your maximum operating temperature for the maximum your reactor can withstand is 200, you have to operate it at 180 degrees maximum, and then keep it for 6 hours, 10 hours, whatever the protocol says. So this is the entire setup, how it looks like. You know, first you have to take this synthesis reactor. This is the body. Then you have to put this hydrothermal synthesis reactor disk bottom. Then you have to place your hydrothermal synthesis reactor chamber body. You put your sample in it. You put the cap. Then again you put the synthesis reactor disk on top. Then you tighten the lid with the rod. Okay. And then you place it in the autoclave machine and set the temperature, that the temperature slowly reaches to 180 degree in every minute 1 degree or 2 degree it will reach, and slowly it will reach 180 degrees, stay for 6 hours, and then slowly it will come down. Okay, so this is how the hydrothermal synthesis works for carbon dots. So here you can see that different carbon dots have been synthesized. You can see on top the size have been mentioned. So 2 nanometer, 3 nanometer, 4 to 9.5 nanometer. And you can see with increasing size, slowly the wavelength also increases. So from purple to slowly you are going towards red with increasing size for carbon dots. So depending on the color of the carbon dot, the fluorescence you are seeing, you can take a guess of what will be the size of the carbon dot. Do you think you can see the carbon dots in SEM? Characterization technique for carbon dots. Okay, you will be able to see something, but then again, it will be very blurred. It will not focus that well. So better to use TEM if you want to see carbon dots, because even if for gold nanoparticles, they are also very small in size, 10 nanometer or less, you basically see a blur. Like I have tried seeing under SEM, you do not get good images. So it is better to go for TEM. So electromagnetic spectrum or the EM spectrum, you can see that electromagnetic spectrum is basically you have when the wavelength is shorter, you have gamma rays, then x-rays, hard x-rays, soft x-rays. Then slowly with increase in wavelength, you're going UV, then visible, then infrared, microwaves, and then radio waves. So these are the name of the waves with from increasing wavelength. So with wavelength increases from gamma rays to radio waves, frequency decreases from gamma rays to radio waves, and energy decreases from gamma rays to towards radio waves. Okay, so energy of one photon, it decreases. So radio waves have the lowest energy and gamma rays have the highest energy, and the more these are known as ionizing radiation. So radio waves, microwaves, infrared, these are non-ionizing radiations, whereas ultraviolet, x-rays, and gamma rays, they are ionizing radiation. So there are different types of scattering of light based on energy. So I think you have heard of the term, I think it was mentioned, elastic scattering and inelastic scattering. So what is elastic scattering? Elastic scattering is total kinetic energy and wavelength of the radiation. They are conserved. That is, you have an electron, and that is, it's absorbing a particular wavelength, getting excited, and then when it is coming down to its ground state again, it is releasing another wavelength. If the wavelength which it absorbed, the excitation wavelength and the emission wavelength are same, then it is known as elastic scattering. Some examples of elastic scattering is Rayleigh, Mie, and Tyndall. What is inelastic scattering? Inelastic scattering is energy is transferred between the radiation and the particle, changing the wavelength. Okay, so what happens? Your electron, it will absorb a particular wavelength, but when it is emitting a wavelength, it emits a different wavelength. The wavelength is different from the one which it has absorbed. So the excitation wavelength and the emission wavelength is different in energy. And why it is different in energy? Some of the energy, it is lost by radiation between the particle. Okay, that is why the wavelength changes. So some examples of inelastic scattering is Raman, Brillouin, and Compton. Okay, so this is what elastic scattering and inelastic scattering means. These are very two important terms because you have to understand which spectroscopy is elastic scattering and which spectroscopy is inelastic scattering. So there are different types of scattering of light, like we mentioned. So Rayleigh scattering, this is a elastic scattering. It occurs when particles are much smaller than the light's wavelength. For example, nitrogen or oxygen molecules. It strongly scatters shorter wavelengths blue, causing the blue sky. So this sky that we see blue, that is because it strongly scatters shorter wavelengths. So you have nitrogen and oxygen molecules in the air. So they strongly scatter shorter wavelengths. That is why you see the sky blue. So this is called Rayleigh scattering. So your particle size is smaller, much smaller than the wavelength of light. Okay. In Mie scattering, which is also elastic scattering, occurs when particle sizes are comparable to or larger than the light's wavelength. For example, water droplets, dust. So as a result, it scatters all wavelengths equally. For example, clouds, they look white because of that. So Mie scattering, either your particle size is same or larger than the wavelength of light. Tyndall scattering, this is also an elastic scattering. What is happening? Light scattering by particles in a colloid or fine suspension. Often used to describe the scattering of light by colloidal particles. So this is called Tyndall scattering. Okay. Then what is Raman scattering? Raman scattering is an example of inelastic scattering. So it is interaction of light with molecular vibrations, which causes a change in energy of the scattered photon. So basically your molecule is vibrating and then it will absorb a particular wavelength, and that vibration, what vibration is occurring, depending what wavelength is being emitted, you can actually map what kind of molecular vibrations are occurring in your material, in your nanomaterial. Okay, so what is the functional group, what kind of molecular vibrations it is undergoing, because each molecular vibration will give you different wavelength of emitted light. So this is Raman scattering. Then Brillouin scattering is another example of inelastic scattering. Here the scattering of light is due to interactions with acoustic waves. This is density fluctuations in a medium. Whereas Compton scattering, which is also an example of inelastic scattering, is high energy scattering where X-rays or gamma rays scatter off electrons losing energy. Okay. So type of scattering is, did you understand type of scattering? Type of scattering, is it clear? Okay. So then we come to types of energy transitions in each region of the EM spectrum. So we talked about different gamma rays, X-rays, then UV, infrared, microwave, radio frequencies. So we're not talking about gamma rays. We are starting from X-rays. So high frequency, high energy, ionizing radiation, and what you have? Wavelength is shorter for X-rays. So here what kind of transition happens? Bond breaking happens. So X-rays, like I said, it is ionizing radiation. So bond breaking occurs in when you expose a material to X-rays. So the methods which use X-rays, one example is X-ray diffraction, which you have already been taught. So what it helps in identification, it helps in crystal structure identification. We will see some examples of crystal structure. I think it was mentioned in the video what kind of crystal structures you have. But I don't know it was elaborated or not. So I have included a small slide for that. And phase identification. Okay. So you have X-ray diffraction. Then you have another characterization technique which is not mentioned in this course, but which is also equally important for certain nanomaterials, that is X-ray fluorescence. This gives you elemental composition of your material. So if you have to find your elemental composition of material, you can go for X-ray fluorescence. Then you have X-ray photoelectron spectroscopy, XPS. This gives you surface chemistry. So I'll give you an example. I think this example was given in the slide for XRD only, that you were shown an XRD peak of graphene oxide and reduced graphene oxide. So you saw a long peak of graphene oxide. Some HKL plane was written. You know what is HKL plane? HKL plane. You know what is HKL plane? You have been taught something called Miller indices. Miller indices. So this HKL plane, I don't know if you remember that slide or not, but there was a picture of the XRD of graphene oxide and reduced graphene oxide. You had a long peak, which showed the graphene oxide, and then that peak shifted to a different HKL plane and much less in intensity. That was the reduced graphene oxide. That was an XRD picture image of it, but this surface chemistry, graphene oxide will have more oxide group and reduced graphene oxide will have less number of oxygen groups on surface. This change in surface chemistry between to confirm whether your graphene oxide has come transformed to reduce graphene oxide, you can do this using XPS. So if you do XPS, you can confirm that yes, your X-ray, your surface chemistry changed. There were more number of oxide on the graphene oxide compared to reduced graphene oxide, and which will be a confirmatory that you were able to synthesize reduced graphene oxide from graphene oxide. Okay, then next region in the spectrum is ultraviolet or visible. This is energy transition is electronic. The method is called UV visible spectroscopy. This has also been discussed in this course. So the energy transition in UV visible spectroscopy, it is electronic. Okay, so the biggest thing is that for a particular sample to be UV active, you need to have conjugation, double bonds. So there are particular transitions that are needed, that electronic transitions, N to pi star, pi to pi star, sigma to sigma star. So there are 3 or 4 electronic transitions that should occur for UV visible spectroscopy. Then only you will be able to get a peak in UV visible spectroscopy. So for that, what if a molecule has conjugation, that makes it UV visible spectroscopy active. If you have a linear molecule without any conjugation, you will not get any peak in UV visible. Visible, you will get peak if there is some color. But UV peak you will not get until and unless you have a conjugation. So there is 3 or 4 electronic transitions which makes the molecule UV active. Then we have infrared. Infrared energy transition is vibrational. So this is used in infrared spectroscopy. Basically, this spectroscopy monitors the vibration of functional groups, and each functional group vibrates at different frequencies. So that frequency is correlated by the I think it is called wave number and intensity. Wave number versus intensity, and then you can understand what kind of functional group is present on the surface of your nanoparticle or nanomaterial, because each surface group will have different vibrational energy. Microwaves, the energy transition is rotational. It is used in a method called microwave dielectric spectroscopy. It has not been mentioned in this course, so we'll not get much into that. And radio frequencies, there are 2 kinds of transitions that can occur. One is nuclear spin, which is exploited in nuclear magnetic resonance, NMR. I think you guys might have heard of NMR. And the other is an electron spin, which is used in electron spin resonance. Okay, so we'll not talk much about microwave and radio frequencies, as mostly our course is X-ray diffraction, UV visible, and infrared spectroscopy. So the characterization techniques for nanomaterials, which has been shown here, is UV visible spectroscopy, PL, photoluminescence or fluorescence spectroscopy. You have studied dynamic light scattering, zeta potential, Fourier transform infrared spectroscopy, scanning electron microscope, energy dispersive analysis of X-rays, also called EDAX or EDX, transmission electron microscope, TEM, transmission electron microscope, which is TEM, atomic force microscope, AFM, and there is another point I forgot to mention, that is XRD, X-ray diffraction. So UV visible spectroscopy, I think you have already studied single beam spectrophotometer and double beam spectrophotometer. Have you studied in detail? Was it explained in detail to you in the course? What is single beam and double beam? There was a difference chart, I think, difference table. But in detail, what is UV visible, like single beam, double beam? Anybody saw instrument? Single beam instrument and double beam instrument? Anybody? Okay. So UV visible spectroscopy, single beam means you have a light source, then you have a lens, grating, and then grating or a prism, and then you have the wavelength selector. So the prism basically it splits the white light into the visible spectrum, and then you will select a particular wavelength and allow it to pass through the wavelength selector and through your sample. So first in single beam spectrophotometer, what you do, you put your reference first. Your reference is basically, suppose you are measuring gold nanoparticles. So your gold nanoparticles is synthesized in water. So you put water in your reference first. Then you what you do is you do a blank calibration and a baseline calibration. Okay, you do a baseline calibration first, then you do a auto blank, and after doing an auto blank you remove your reference, you put your sample in the same, remember you have to use the same volume of sample. So here the cuvette represented is a 3 ml cuvette. You should fill it 2/3, so not more than that. You basically you have to make sure that you have the detector at 180 degree. So your detector is at 180 degree. So detector is at 180 degrees. So your light source, suppose this is the cuvette sample holder. You have your source from here, your light source, and the detector is at 180 degree for UV visible. Okay, so you have to just make sure that you have enough volume that the light passes through your sample. It should not be like half of the light is passing through your sample and then half is passing through just the cuvette. Okay, so only that much amount of sample you need. You do not need to fill completely 3 ml. So for that, as a rule, we just fill up 2/3 of the volume, and then you pass the light and the detector is at 180 degree, and it will give you a value for absorbance. So there are two modes of UV visible spectroscopy if anybody has used. One is the transmission mode, the other is the absorbance mode. UV visible spectroscopy always measures in the transmission mode. So the light that is passing through your sample, it measures how much light is transmitted. It doesn't measure how much light is absorbed. The value is always generated as transmittance, but it uses the formula. The formula I think is mentioned in the course. It uses the formula to calculate the absorbance. So if you're using the UV visible spectroscopy in absorbance mode, it basically uses that formula to give you the value of absorbance. But UV visible spectroscopy is always, it measures value in transmittance mode. Okay, so if for example you are giving 100%, you're giving 100% light, and the intensity, the transmittance is only suppose 10%. So it will subtract and say that absorbance is 90. And if your transmitted light is 100 and your incident light is 100 and your transmitted light is 90, that means your absorbance is 10. So like that, it calculates using that formula. Okay, so this is the single beam spectrophotometer. Whereas the advantage of double beam spectrophotometer is that you keep your reference sample there. You do not remove your reference sample. You just split the light source into two, which will simultaneously pass your reference sample as well as your test sample, and then immediately subtract the reference sample, the absorbance of the reference sample from your test sample, and give more accurate results. So mostly we use double beam spectrophotometers in labs. So that is the difference between the double beam and the single beam. But what you should do is, when you are doing blank calibration, you should place both reference samples in both cuvettes in double beam. So when you are using double beam spectrophotometry, don't keep a reference sample only in one cuvette and then do a auto calibration, a baseline correction and blank. blank calibration. You should put reference sample in both the qubits, then do the baseline correction and auto blank, then remove one qubit from reference sample and put your test sample in that. And then you can keep changing your test sample, keeping one reference sample qubit there. Okay, so this is one thing you should remember while using a double beam spectrophotometer. For photoluminescence spectroscopy, so here you can see in photoluminescence spectroscopy, you have a absorbance maxima, you have a fluorescence, and then you have phosphorescence, and you can see the wavelength is different for each. So absorbance is your excitation. So there is a thing which is said, you can use UV visible to find out the excitation maxima. So if you have a fluorophore, you can perform a UV visible spectroscopy. The absorbance of the fluorophore is the wavelength, excitation wavelength of your fluorophore. Okay, so absorption maxima and excitation maxima is basically same. Compounds which are not fluorophores, their absorbance wavelength will not give you any emission wavelength, but compounds which are fluorophores, their absorption maxima is their excitation maxima. So if you excite the fluorophore with that wavelength, you will get an emission wavelength. You will get an emission wavelength which is slightly shifted at higher wavelength. So this shift is called what? Anybody remembers what this shift is called? I think you have studied what this shift is called. It is called a Stokes shift. The excitation maxima and the emission maxima, they are slightly shifted. The emission maxima is slightly shifted. That difference in the peak is called Stokes shift. So what is happening? The phenomenon of temporary light absorption and subsequent light emission is called photoluminescence. Photoluminescence, which occurs by virtue of electromagnetic radiation falling on matter, may range from visible light through UV, X-ray and gamma radiation. Photoluminescence is a process in which a molecule absorbs a photon in the visible region, exciting one of its electron to a higher electronic excited states, and then radiates the photon as the electron returns to a lower energy state. So this phenomena we will see in a diagram, very famous diagram, which is called the Jablonski diagram. We'll come to that Jablonski diagram. So in the PL process, there are mainly three things happening. One is excitation, which is what? Excitation is, here is one electron. You are providing a particular wavelength, which provides it enough energy to get excited to this, to go up to this excited state. It gets excited to this state. Then what happens is non-radiative relaxation. Non-radiative relaxation is what? No wavelength is emitted. So basically it loses some of its energy and come down. So basically in excited states, what you have in conduction band, you have different levels, different excited states. So if it goes to a higher excited state, it will come down to the lowest excited state first. That is known as non-radiative relaxation. No wavelength is released there. No wavelength is released. So this energy loss, so it does expend some energy to come down to the lowest excited state. So this energy is expended as rate, and then it comes back from the lowest excited energy state, releasing a luminescence photon back to the valence band. Okay, so this is why your energy between the emission spectra and the spectrum and the excited spectrum and the emission spectrum is different. So this green one represents your excited spectrum. It will give you an excited spectrum, though at this peak the molecule absorbs a particular wavelength. And the emission spectrum is shifted because when the electron is in its higher excited state, it comes to the lowest excited state by non-radiative relaxation. So some energy is lost. That is why it shifts towards the higher wavelength, the excitation, the emission spectrum. Okay, so these are the three main processes that is happening: excitation, relaxation, and emission. So in the PL process, what is happening? The photo excitation causes the material to jump to a higher electronic state and will then release energy photons as it relaxes and returns to a lower energy level. The emission of light or luminescence through this process is called photoluminescence. So again, it is shown here. S0 is your ground state. The electron absorbs a particular wavelength of light, gets excited to a state S2. Then this small arrow, this number 2 step is your non-radiative decay, where it comes down to the lowest excited state, S1. And then from there, it comes back to the ground state, S0, by emitting a photon of higher wavelength. So here you can see the blue one is your excitation maxima and the red one is your emission spectrum. And you can see there is a difference between the two peaks. So this difference, which is represented here as B, this is called Stokes shift. You will always have a Stokes shift like this. So what you should do is, this Stokes shift will happen. So you should avoid any interference from your excitation spectrum. So for that, what you should do is, when you're performing PL spectrum, you know your absorption maxima is at, suppose your absorption maxima, you know it is at maybe 520 nanometer, for example. 520 nanometer. What you should do is, you should start measuring your excitation spectrum 20 to 40 nanometer ahead of that, so that no interference comes from your absorption excitation spectrum. So you should always start your excitation spectrum calculation 20 to 40 nanometer more of your excitation wavelength. Okay, so in PL process, PL is a process in which a molecule absorbs a photon in the visible region, exciting one of its electron to a higher electronic excited state, and then it radiates a photon as the electron returns to a lower energy state, because excited states are unstable. If the molecule undergoes internal energy redistribution after the initial photon absorption, the radiated photon is of longer wavelength, that is lower energy, than the absorbed photon. Okay, so here you can see valence band. This is the band gap energy. So the luminescence photon, the wavelength of that is your band gap energy actually. So excited photon goes to higher excited energy states. Then it undergoes again non-radiative relaxation. We have already discussed this. And then it comes down to the most stable state. So this is the Jablonski diagram. Here you can see that states are represented. This is your S0 is your ground state. Here you can see 0, 1, 2, 3, 4, 5. These are different vibrational energy states. Here you can see it is written vibrational energy states. And S1, S2, these are excited singlet states. Okay. T1 is excited triplet states. So electron, when after absorbing a wavelength of light, which is suppose h mu, it can get excited to S2 level. Then it will undergo internal conversion. This is a phenomena, non-radiative decay or internal conversion, and come down to S1. Okay. From there, either it will not radiate any energy and come down to the ground S0 state. This is known as quenching, because the whatever energy is being released, that is being absorbed by some other molecule in the vicinity. It can undergo some internal conversion. This is also non-radiative and come down to the state. And when you will get fluorescence, when it is radiative, when the molecule will release a wavelength which is different from the absorption wavelength, okay, which is h mu emission here. Then it is known as fluorescence. So from the singlet state, it is coming down to the ground state. That is fluorescence. But sometimes what happens, electron, instead of coming down directly from the singlet state to the ground state, it can go inter-system crossing to the excited triplet state. In the excited triplet state, if the molecule goes, then again two things can happen. From the inter-system crossing, from the excited triplet state, it can undergo internal conversion, not radiate any photon and come back to the ground state, or it can radiate a photon of a different wavelength and come down to the ground state. Now, this phenomenon is not fluorescence. This is called phosphorescence. Okay, so phosphorescence is also known as delayed fluorescence. So fluorescence is, you can see immediately, phosphorescence is something which takes time. So fluorescence is as soon as you suppose you have carbon dots, you switch on the UV, you see the fluorescence. You switch off the UV, immediately it switches off. But phosphorescence is you switch on a compound which shows phosphorescence. You switch on the UV light, it will take some time to give the phosphorescence. But when you switch it off, it remains. The switch of the UV light, you will see some amount of fluorescence you will see, but that is not the fluorescence phenomena, that is phosphorescence, which is known as delayed fluorescence, as it takes more time by undergoing this intersystem crossing to triplet state. So, difference between fluorescence and phosphorescence. Fluorescence is spontaneous emissions of electromagnetic radiation. Phosphorescence is delayed emission of electromagnetic radiation. Fluorescence is glow of fluorescence stops right after the source of excitatory radiation is switched off. Phosphorescence is an afterglow with durations of fractions of a second. Up to hours can occur. Like I said, if you switch off the light source, excitation source, after that there will be an afterglow. That is phosphorescence. Fluorescence is light produced by the absorption of UV light, resulting in immediate emission of visible light. Phosphorescence, light production by the absorption of UV light, resulting in the emission of visible light over an extended period of time. Fluorescence is ground state to excited singlet state and back. Phosphorescence is ground state to excited singlet state. Then it undergoes intersystem crossing to triplet state, and then it comes back to the ground state. Fluorescence example is highlighter pens, fluorescent lighting, fluorescent dyes in detergent, and phosphorescence examples is objects coated with phosphorus. So PL or fluorescence spectroscopy, this is a non-destructive spectroscopy technique commonly used for the study of intrinsic and extrinsic properties of both bulk semiconductors and nanostructures. PL spectroscopy is when light energy or photons stimulate the emission of a photon from any matter. Okay, PL spectroscopy is a contactless, versatile, non-destructive, powerful optical method of probing the electronic structure of materials. The intensity and spectral content of this photoluminescence is a direct measure of various important material properties. PL spectroscopy gives information only on the low-lying energy levels of the investigated system. During a PL spectroscopy experiment, excitation is provided by laser light with an energy much larger than the optical band gap. Band gap, here you can see this is the band gap between the ground state and the excited state. So the laser light provides energy which is much larger than the optical band gap. Okay, so the photo excited carriers consist of electrons and holes, like in quantum dot. Remember, we were talking about electron hole pair. So the exciton thing also is applicable here, which relax toward the respective band edges and recombine by emitting light at the energy of the band gap. The quantity of the emitted light is related to the relative contribution of the radiative process. Radiative transitions in semiconductors may also involve localized defects or impurity levels. Before the analysis of the PL spectrum leads to the identification of specific defects or impurities, and the magnitude of the PL signal allows determining their concentration. The respective rates of radiative and non-radiative recombination can be estimated from a careful analysis of the temperature variation of the PL intensity and PL decay time. At higher temperatures, non-radiative recombination channels are activated and the PL intensity decreases exponentially. That is why when you're operating a fluorescence spectroscopy instrument, you should not be operating it for a long time. If you see that your instrument is heating up, that means your temperature is rising. It will start giving errors in your PL intensity. So you should do the analysis, check whether your instrument is heating up or not. Switch off the instrument, let it cool down, then again start measuring. So you should not do PL spectroscopy for longer durations if your instrument is heating up, because then you will get non-radiative recombinations. So the PL intensity will decrease. So in UV visible, the what kind of cuvette you use in UV visible and what kind of cuvette you use in fluorescence spectroscopy? In UV visible, what kind of okay. So in UV visible, you use a two-walled quartz cuvette. Why quartz is used? What kind of material? I think it is also already mentioned in the course. So in UV visible, you use a two-walled quartz cuvette as the detector is at 180 degree. Why the detector is at 180 degree? Because transmitted light is always at 180 degree. That is why the detector is at 180 degree. However, for fluorescence spectroscopy, you can see the setup here. Fluorescence spectroscopy, the detector is at 90 degree. Why? Because you can see your light source is here, many wavelength excitation monochromator. So your excitation monochromator will select a particular wavelength which will excite your sample. Your sample cell is here. So this is your lambda excitation, one wavelength selected by the excitation monochromator. Then the luminescence or fluorescence will be at many wavelengths. Then you select a emission, you have an emission monochromator here, which will select a particular wavelength. That is your lambda emission, and then your detector will detect it. Basically amplify it. So here what happens is, why the detector is at 90 degree? Why not at 180 degree? In UV visible, your detector was at 180 degree because your transmission light is 180 degree. But in this sample cell, your detector is fluorescence spectroscopy, your detector is at 90 degree. Why? Because in the sample cell, fluorescence is given in all directions. Transmitted light is only at 180 degree, but fluorescence is given in all directions with equal intensity. So if you place your detector here at 180 degree for fluorescence spectroscopy, you will get both transmitted light. Some light will not be absorbed by your sample, so you will get both transmitted light as well as your lambda emission, your emitted light, your fluorescence. So it will interfere, the transmitted light will interfere with your lambda emission. That is why the detector is placed at 90 degree, because transmitted light is negligible in this direction. It's almost not there. So that is why the detector is at 90 degree for fluorescence spectroscopy. Then we have DLS. In DLS, what you do is you measure the hydrodynamic diameter. So in TEM, you get the actual size of your sample, whereas DLS gives you hydrodynamic diameter. So you have you use the Stokes-Einstein equation to basically calculate the hydrodynamic size of a material. So in a DLS, what you do is you have a sample in which your particles are undergoing Brownian motion, that is random motion, and then you have a laser source. The depending on the velocity of your particle, the laser will be scattered. Okay, so if your particles are large, there will be a small scattering angle, because the particles will be moving with small velocity and the scattering angle will be small. So depending on that, it correlates the velocity of the particle with the size of the particle. So if the particles are small, then they will be moving much faster in solution, the velocity will be more, and the scattering angle of the laser light source will be more. Okay, so this is how using the Stokes-Einstein equation, the DLS measures the hydrodynamic size. You should always remember, whenever you're talking about size using size which is measured using DLS, you should always say hydrodynamic size, because the actual size you see under TEM, transmission electron microscope. And what do you mean by hydrodynamic size? Hydrodynamic size is the size of a nanoparticle along with your bound stabilizers. That is the size of your, that is known as the hydrodynamic size. Okay, so this is DLS. Also, I forgot to mention, for fluorescence spectroscopy, you have a 4-walled cuvette because fluorescence is in all directions. So you use a clear 4-walled quartz cuvette for fluorescence. You use a 2-walled quartz cuvette for what is it, for UV visible. For dynamic light scattering, you can use disposable cuvettes as well as permanent cuvettes. Mostly we use disposable cuvettes. They are made of a compound called polystyrene latex. So polystyrene latex is basically a compound, since they are use and throw, but we use it multiple times. You should be very careful that the cuvettes do not get scratched. If there are any scratches on the cuvette, then each scratch will be scattering your laser light. So then the instrument will think that it is a particle. So if there are any scratches, you're supposed to change the cuvette. And the polystyrene latex is a disposable cuvette. So never use any organic solvent to clean your cuvette. If you use polystyrene latex cuvette and you clean it with organic solvents like acetone, immediately your transparent cuvettes will turn cloudy and your cuvette will be destroyed. So always don't use any nanoparticle suspended in any organic solvents, or clean your cuvettes in organic solvents while performing DLS. DLS or zeta potential. So zeta potential also, the cuvette is made of polystyrene latex. Here you use electrophoresis. I think it's already been mentioned, you use electrophoresis to measure what is the charge on the surface of your nanoparticle. So you have a value of minus 30 millivolt to plus 30 millivolt. So if your particle has charge less than minus 30 millivolt, then it is stable, or if it has charge more than plus 30 millivolt, then it is stable. It is considered to be stable. So what is the zeta potential? So you can see here is the nanoparticle. You have a strong charge, bound charge. This is known as the surface potential. Okay, so the charge measured at this point is known as the surface charge. Okay, so these are your solvent molecules which is bound. Okay, so then you have another layer which is known. So this first layer is known as the Stern layer. The second one you have is loosely bound particles, loosely bound ions, solvent ions, which move with your particle. So the first is the surface charge. Then the Stern layer is made of solvent molecules which are tightly bound to the surface of your nanoparticle. And the potential at this Stern layer is called Stern potential. Then you have the next layer, which is loosely bound solvent molecules. Some of the solvent molecules are exchanged between the surface of the nanoparticle and the solution, but these charges also move with your nanoparticle. So this surface is called the electrical double layer. This surface, Stern layer, and this second layer, both are called the electrical double layer. And this surface is the potential at the slipping plane, which is the outside dotted line you can see. The potential at the slipping plane is called zeta potential. So the zeta sizer software at the zeta potential mode actually measures the zeta potential value. That is the potential at the slipping plane. Then outside that, the solvent molecules, they do not travel with your nanoparticle. So the equation here, it is represented how the software uses the Smolowski model to measure the zeta potential of a nanoparticle. Then we come to FTIR spectroscopy. FTIR spectroscopy. So there is a selection rule for FTIR spectroscopy, that which molecules are FTIR active. How you will understand? So if a molecule will absorb infrared radiation, there will be a change in vibrational states that are associated with a change in the dipole moment of a molecule. So change in dipole moment, when a molecule absorbs IR radiation, there has to be a change in dipole moment. Okay, so if there is no change in dipole moment, then the molecule is IR inactive. If there is a change in dipole moment, then only it will be IR active. So it is represented by the formula mu equals to QR, where mu is the dipole moment, Q is the electric charge, and R is the direct expected distance of that charge from some defined origin of coordinates from the molecule. So there are two types of vibrational modes. One is change in bond length, which is called stretching, or bond angle, which is called bending. Okay, so stretching vibrations, you can see there are two kinds of stretching vibrations here represented, symmetric and asymmetric. So symmetric stretching vibrations will not give you any change in dipole moment. So this is any molecule which is showing symmetric stretching will be they will be IR inactive. Okay, asymmetric stretching will give you a change in dipole moment. Bending vibrations, there are different kinds of bending vibrations. One is in plane rocking, in plane scissoring, out of plane wagging, and out of plane twisting. So basically they're called rocking. Rocking, you can see they both the molecules are moving towards in the same direction. Scissoring is the two groups are coming closer and then moving up far apart. Out of plane wagging is both the functional groups, they're coming either towards you or going away from you. And out of plane twisting, twisting is basically both the groups are going opposite direction. Okay, here an example has been given for anti-symmetric, symmetric and scissor bending of H2O. The molecule shown here is H2O. So here you can see so degrees of freedom. So how you will calculate how many total are there. So you have to calculate how many linear, non-linear molecules. So translational is 3, 3, rotational is 2, 3, and vibrational, how you calculate 3n minus 5. For non-linear molecules, the formula is 3n minus 6. So here for water, it is a non-linear molecule. So you have to, for calculating the vibrational, number of vibrational modes, it will be 3n minus 6. Okay, so total for linear you will get 3n, and for non-linear you will get 3n minus 6. So these two formulas you should know the linearity of the molecule. So linear molecule, for example, is CO2. So that vibrational mode will be, calculation will be 3n minus 5. Whereas for non-linear molecule, you have to follow 3n minus 6. The example for non-linear molecule here is H2O. Okay. Then we have SEM, scanning electron microscopy. So scanning SEM gives you topography, surface. So surface features of an object or how it looks. It gives texture. Surface, you can see morphology. You can see the shape and size of the particles making up the object. You can get composition, the elements and compounds that the object is composed of, and the relative amounts of them. This is actually the EDAX mode of SEM. Crystallographic information, how atoms are arranged in the object. So there are two types of electrons which are generated in SEM. One is called the secondary electrons and the other is called the backscattered electrons. So these are also the two modes in which SEM operates. Secondary electrons, they are generated from collision between the incoming electrons and the loosely bonded outer electrons. They are of low energy, and only the secondary electrons are generated close to the surface. They escape. Backscattered electrons is a fraction of the incident electron is retarded by the electromagnetic field of the nucleus, and if the scattering angle is greater than 180 degree, then the electron can escape from the surface. They are high energy, but very few backscattered electrons are generated compared to secondary electrons. So mostly when you go to do SEM, secondary electrons are measured. Very few times backscattered electrons are measured because very less number of backscattered electrons are there. So intensity is less, so the image contrast will also be less for backscattered electrons. So here you can see the secondary electron detector, and there will be another detector for backscattered electrons. So two detectors. So backscattered electron detector is here and the secondary electron detector is here. Okay. Then you have EDAX mode in SEM, which is energy dispersive analysis of X-rays. In EDAX, what happens is you have a nucleus and you have different shells, electron shells, K, L, M, N. So when an electron beam is comes and hits a electron at an inner shell. For example, here it is shown the electron beam goes and hits the K shell. the electron is thrown out of the K shell. As a result, there is a vacant spot here. So what happens? Electron from a higher energy level falls into this lower energy level, and energy, radiation energy is released. This radiation energy is calculated and is correlated with different elements, because each element, the energy released is different. So if for example the electron falls from L shell to K shell, then it is called K alpha. It falls from M shell to K shell, then it is called K beta. So depending on each wavelength which is released, different elements will have different wavelengths, and that is how it is quantified, and it gives a percentage of how much of that element is present in the sample. Okay, so this is the principle for EDAX. The incident beam may excite an electron in an inner shell, which ejects it from the shell, ejecting it from the shell while creating an electron hole where the electron was. Okay, so the electron is getting displaced. There is a hole. There is a positive charge here. An electron from an outer or higher energy shell then fills the hole, and the difference in energy between the higher energy shell and the lower energy shell may be released in the form of an X-ray. The number and energy of the X-rays emitted from a specimen can be measured by an energy dispersive spectrophotometer. So this is basically fit into SEM. Sometimes even TEM nowadays come with EDAX. So you can do an elemental analysis on TEM as well. So this is basically a semi-quantitative elemental analysis. For quantitative analysis, I think I mentioned was XRF. So in transmission electron microscopy, you can get a selected area diffraction pattern as well using TEM, depending on whether your molecule is crystalline, amorphous, or polycrystalline. You will get different kinds of set pattern as shown here. Polycrystalline, you get multiple dotted rings. Crystalline, you will get single dots, and amorphous, you will just get a blur. So depending on that, you can understand the nature of your sample. And here is shown a reaction, sample reaction volume with electron beam, which is very important for different techniques. So when your electron beam comes and hits your sample, you can see that backscattered electrons are basically near the surface of the sample. So they give you topographical image, that is surface image. Then lower than that is lower than the secondary electron is the backscattered electron, which gives you the phase difference. Then lower than that is the characteristic X-ray, that is gives you thickness, atomic composition. Below that, if is continuum X-ray, Baumstrahlung, where which is used for X-ray diffraction techniques. Exactly at the surface, above the is the auger electron, which gives you surface atomic composition. Then at the end of the surface, you get is cathodoluminescence, that is gives you electronic states information. So all the above ones are for surface, whatever is getting striking the surface and is reflected back. But if the electron beam passes through, okay, transmitted electrons. So if the beam passes through, then they are transmitted electrons. They give you morphological information. So SEM gives you a 3D image, whereas TEM gives you a 2D image. Okay, then you have inelastic scattering, which gives you composition and bond states. You have elastic scattering, which gives you structural analysis and HR imaging. And then you have incoherent elastic scattering. So this image is very important to know what kind of technique you will use for different kinds of information you need. You need topographical image, you have to go for secondary electron. You need phase difference, you need backscattered electron. You need to do XRD, then you have to use, I think you have already mentioned Baumstrahlung in your course. Then you have X-ray diffraction, XRD. So XRD, basically this image I said that you have to know the crystal structures. So these are known as Bravais lattices. There are 14 Bravais lattices. So 4 types of unit cell. One is known as primitive, which is represented by P. One is body centered, represented by I, face centered by F, and side centered by C. Okay, then you have 7 crystal classes. So all total of them will make 4 types of unit cell plus 7 crystal classes, you get 14 total Breves lattices. Let's see how many are there. First one is cubic. In cubic, what is happening? Your A, B, C is equal and alpha, beta, gamma is equal to 90 degree. Then it falls under cubic. So cubic is having both primitive body centered and face centered. You should remember that cubic does not have side centered. Okay, so these are certain, and you can see the arrangement of atoms in primitive only in the corners. In body centered, in the center of the cube, there is one atom apart from the edges. Okay, apart from the corners. In face centered, every face of the cube has a atom in the center and at the corners. Okay, then you have tetragonal. Tetragonal is A is equal to B, but it is not equal to C. Alpha, beta, gamma is equal to 90 degree. So here you again have two types. One is primitive, that is only on the corners of the cell. Then you have body centered. Body centered is again at the center. Apart from the corners, you have one exactly at the center of the cell. Orthorhombic is A is not equal to B is not equal to C, but alpha, beta, gamma is equal to 90 degree. So here you have primitive, body centered, face centered, and side centered. Side centered, you have already seen primitive, body centered, face centered. What is the difference in side centered? Side centered, you can see the two side faces have a atom at the center apart from the edges of the edges of the unit cell. Hexagonal is A is equal to B but not equal to C. Alpha, beta is 90 degree but gamma is 120 degree. Okay, so this hexagonal has only primitive structure, that is only on the vertices of the cell. Then trigonal is A equals to B equal to C, but alpha, beta, gamma is not equal to 90 degree. Here also you have only the primitive one, that is only on the vertices. Molecule arrangement only on the vertices. Then you have monoclinical. Monoclinical is A is not equal to B, not equal to C. Alpha, beta, gamma is alpha and gamma is 90 degree. Beta is not equal to 120 degree. So here you get only primitive and side centered. Here you can see the side centered, the difference from orthorhombic and the monoclinic is the side centered atoms. Okay, the cell, if you just make it upright, then it is monoclinical. But the angles are different. If you notice, different between orthorhombic and monoclinical is the angle of alpha, beta, gamma is different. Okay, triclinic is A is not equal to B, not equal to C, and alpha, beta, gamma is not equal to 90 degrees. So you have only the primitive cell. So these are certain things that you should remember. That is why I included this slide for XRD, that in cubic, what kind of atomic arrangements are there in unit cell, tetragonal, what is there, orthorhombic, what is there, how the unit cell looks like in cubic, tetragonal, orthorhombic. So that is why this is important for your XRD. Okay, because for gold nanoparticles, like I mentioned in previous class, it is actually face-centered, FCC structure. So FCC, face-centered cubic. FCC means face-centered cubic. So gold nanoparticles will come under this one, F and cubic. Okay, this cubic, third one. Then last we come to atomic force microscopy. Atomic force microscopy is basically you have a micro cantilever and you have the sample. Your sample has to be very smooth. There should not be too much roughness, or else if the tip is very delicate, it can break. So you have a piezo element, and what happens is you have a laser source which falls on the surface of the cantilever. Okay, and the cantilever has a very sharp tip which has a single atom. The tip atoms you can see has a single atom, and the force between the surface, that is your sample surface atoms, and the tip atom is actually measured. So what happens? Your surface atom, suppose your tip atoms is positive charge and your surface atom is negative charge. So if the tip atom is attracted towards your surface atoms, then the cantilever will bend down, and accordingly the laser light will be deflected and the photodiode will calculate it. Okay, so that is how the cantilever moves. If the surface atom is positively charged and your tip atoms are positively charged, then it will repel, then the cantilever will move up. So again, the laser source will be deflected in a different direction and the photodiode will calculate that. So this is how atomic force microscope usually measures surface roughness. Okay, so there are three modes of AFM operation. One is contact mode, non-contact mode, and tapping mode. So non-contact mode is the cantilever will just it will not be raised up. It will just slide on the surface. So a lot of damage occurs to the cantilever. So contact mode is usually avoided. Non-contact mode is your surface, your cantilever will not touch the surface. It will just hover close enough and measure forces of attraction and repulsion, which I just mentioned. But non-contact mode usually is not that accurate in measuring surface roughness. So the mode that is mostly used is tapping mode, that the cantilever will tap on your surface of your material, and then the laser source is deflected, and the photodiode will give you the estimation of the surface roughness or smoothness. Okay, so that is the use of your AFM. So if you need a material for which you need enough amount of surface roughness, so this surface roughness you can measure using AFM. Okay, another, like I said, I will give an example of CNT. So CNT is used nowadays at the tip of this cantilever, micro cantilever of AFM, to more accurately, because the CNT is very conductive, very minute, very thin, nanoscale. So it very efficiently gives you more accurate surface roughness measurements. So nowadays CNTs are very actively used at the tip of micro cantilevers for AFM. So that is the example I wanted to give for CNT. So thank you. Any questions you have for today's class? Any questions? Anybody has any questions?
Your slides are available on the course, right?
My slides are, I would not say available on the course. I think I sent a mail out to everybody with a folder link and a YouTube link. So the video will be uploaded in the YouTube link, and the slide I'm uploading in that Google Drive.
Okay, I will
Okay.
check. Thank you.
Please check the mail if you received it or not. If you didn't, I will again mail this one.
Okay,
I'll
I'll
upload
just
this
check.
slide on that folder.
I'll check. Yeah.
Okay.
Thank you.
Okay. Thank you. Any other questions or queries? Okay, so if you have no other questions or queries, today I will be ending my session. We will meet again next Saturday, same time, and the same Google Meet link. So thank you all for joining. You may now leave. Thank you.